Now I want to take a look at how we define and talk about lines in space when we have more than one independent variable. If I have a function of one independent variable, then the points on a line are defined as ordered pairs. And I have two variables, one of which is dependent and one of which is independent. In cases where I have more than one independent variable, so in R3 space, I have two independent variables and a dependent variable, I tend to use 3 points to describe a surface. But that doesn't mean that I can't work with lines in R3. While a line is the simplest curve that I can work with in R2, the simplest geometry that you work with in R3 involving all three variables is a plane. But there can still be lines within R3 if I have a situation where I can define 2 points and just talk about the line that connects the two of them. Keep in mind that we learned in algebra that a line is defined by two distinct points and that that's a unique line. In R3, my two distinct points are ordered triples rather than ordered pairs, and I have two independent variables. The easiest way to work with lines in space and define them is done using vectors in R3. If I define a point in space, let's call it P sub naught, and it has the coordinates x naught, y naught, z naught, I can construct a vector from the origin to that point, and I'll call that vector r sub naught with components x naught, y naught, z naught. And then I can look at another point in space. I'll call that P with coordinates a, b, c. And the vector that goes between the origin and my second point, I'll call r sub 1, and it's equal to a scalar t times the vector with components a, b, c. Now I can construct a line between p naught and p, and because I'm using the vectors to define the point in space, I can look at this and say, that looks a lot like a resultant. And remember then, resultants in vectors are the sum of the two vectors, so that I can express my line as a vector component equation that is given by a vector with components x, y, z is equal to the vector with components x naught, y naught, z naught plus a scalar t times a vector with components a, b, c. I can also write this in a vector equation using r is equal to r naught plus tv, where r naught is my original vector for the original point, and v is the vector with components a, b, c. And t can range between negative infinity and infinity. In addition to these component and vector equations, I can also define the line using parametric equations for the x, y, and z components of my vector. X is equal to x naught plus at, y is equal to y naught plus bt, and z is equal to z naught plus ct. Now that I know what the equations are that I can work with, let's work an example. Let's find both parametric and vector equations for a line that passes through the point with coordinates -3, 2, and -1, and lies in the direction of the vector v with components 1, -2, and 0. The point -3, 2, -1 is my p naught point, and I'm going to write the r naught vector for that from the origin to that point, given by a vector with components -3, 2, -1. My p is that original point, and v is the vector I'm going to multiply by a scalar t, and t times a vector v is equal to t times a vector with components 1, -2, and 0. So my general R vector will be given by the sum of a vector with components -3, 2, -1, plus the scalar t times a vector with components 1, -2, and 0. If I add those component by component, I get R is equal to a vector with components -3 plus t, 2 minus 2t, and -1. This is my vector equation for this line. My parametric equations are the components themselves. X is equal to -3 plus t, y is equal to 2 minus 2t, and z is equal to -1. Let's work another example. Let's find the vector and parametric equations for a line that connects 2 points. P0 has coordinates -1, -8, -4, and P1 has coordinates -9, 5, and -3. P0 is my original point, so my R0 is the vector with components -1, -8, and -4, and my t times v is t times a vector with the components -9, 5, and -3. My general R vector is given by the sum of these two vectors. When I add the terms of each component separately, I get a vector with the components -1 minus 9t, -8 plus 5t, and -2 minus 3t. The parametric equations are the components of that R vector. X is equal to -1 minus 9t, y is equal to -8 plus 5t, and z is equal to -2 minus 3t. So now you get to try it. Pause the video and find the vector and parametric equations for the line that connects the point P0 with coordinates 3, -2, -4, and P1 with coordinates -2, 2, and 1. When you're ready, restart the video to check your understanding. In order to solve this, I want to first write out my R0 vector. That's a vector with the components 3, -2, -4. My VT term is going to be t times a vector with components -2, 2, and 1. My R vector is the sum of these two vectors. When I add those term by term, I get a vector with components 3 minus 2t, -2 plus 2t, and -4 plus t. The parametric equations for this are the components of my R vector. X is equal to 3 minus 2t, y is equal to -2 plus 2t, and z is equal to -4 plus t. This is how we define a line in R3 space with vector equations or parametric equations. Let me know if you still have questions.